Okay, pre-cal students, in this video, we will be analyzing graphs of functions. In the past, we analyzed the actual functions, not their graphs. In other words, we looked at equations, and we did different things to those equations. Now, we are going to look at the graphs and analyze them. Your heading for today is Analyzing Graphs of Functions, Lesson 1.2. Be sure to include today's date. Analyzing Graphs of Functions, Lesson 1.2. Analyzing Graphs of Functions, Lesson 1.2. We will be looking at these graphs today from many angles. First, let's start off by looking at the domain and range of a graph. Please take really good notes. Alright, now, I don't expect you to take time to pause the video and copy down all of the graphs that we're going to look at today. That would just take too long. So, I'm giving you the page numbers. In your notes, I would write down the page number and then whatever figure this is. For example, if you turn your books to page 79, you're going to see this is called figure 1.6. So in your notes, I would write page 79, figure 1.6, and then take some notes, okay? Now, look carefully. When I ask you to tell me the domain of this graph, domain refers to the x values, okay? So watch what I do. I go to the far left of the graph, and I draw a line that goes through the graph vertically and crosses through the x-axis. That's how I teach my students to do this, and here's why I teach them to do this. Students sometimes get confused as to what values they're dealing with when it comes to domain and range. Now, I'm going to draw a line through the end of the graph over here, and notice it's going to go through 5. Now, that means the graph ran from here all the way to here on the x-axis. So that's your domain. So your domain starts at where on the x-axis? -1, and goes all the way to where on the x-axis? 5. However, please notice something. Notice how this point here is closed right here, shaded in, and this point is not. So when you draw your domain, you're going to say -1 with a bracket, because -1 is inclusive, and when you put 5, you're going to put a parentheses, because the graph went all the way up as close as you can get to 5 without including 5. So there is your domain. Okay, the domain runs on the x-axis from -1 to 5, inclusive and non-inclusive. Take a really good look at that, okay, students? You need to understand that. Now let's talk about the range. The range, of course, is the y values. So now I'm going to draw some horizontal line. So go to the highest point on the graph, which is here, and draw a horizontal line. Now go to the lowest point on the graph, which is right here, and draw a horizontal line. Okay? Now, think about it, guys. Just like here, we went from left to right, from the negative side to the positive side, with the domain here of your y value, the range that we're going to deal with is going to start with the negative part of the y-axis and go up to the positive. Now guys, that should not be confusing. That's just like the domain. Like I said a second ago, the domain started from the left, the negative side, and went to the right. So the range is going to start with the negative side and go to the positive. So the lowest part of the graph on the y-axis, it goes all the way down to -3. That's why you drew a horizontal line, so you can see how far down the graph went. It went to -3, okay? Now, it went all the way up to +3. Also, notice this point is shaded in. It's inclusive, and this point is shaded in, inclusive. So the range of this graph would be bracket -3, comma, +3, bracket. So the domain ran from -1 to 5. Inclusive, non-inclusive. The range ran from -3 to 3. Both are inclusive. notes, please feel free to do that. Now, sometimes graphs will be unbounded. Let me show you a couple of examples, okay? Please take some really good notes. Copy down a parabola, please. A parabola. Now, let's talk about the domain, okay? You should know by now when you graph a parabola, even though it looks like it's straightening out, it always continues to get wider, little by little. So, unlike this last graph, there is a stopping point to the left, right here. There is a stopping point to the right, right here. This graph has no stopping point to the left and no stopping point to the right. So there's really no vertical line I can draw. It just goes on and on and on this way, on and on and on this way. Do you see that okay? So the domain would simply be negative infinity to positive infinity. And of course, when we use infinity, we always use parentheses. Okay? Now, let's talk about the range for a second. Okay? Let's say here's the low point right here. And let's say that ordered pair was, I don't know, a half, comma, -2. Okay? I'm just making this up as I go. Now, there's no way I can draw a horizontal line up here because these lines keep going up and up and up. They never stop. Do you see that? So there's no way, like the last graph, it stopped. That's as high as it went right there. That's not the case with this graph. So there is no horizontal line you can draw going across. However, there is a horizontal line you can draw across the bottom. And when you draw it, notice it goes through -2. So the range, remember, you always start with the negative numbers first. So the range is -2 inclusive, going on up and up forever. So there we go, -2 to positive infinity. That would be the range. I hope this is making sense. Okay, now let's take this one more step further. Let's pretend our original graph. Just kind of watch this. Take some notes if you want to. But let's say that our original graph had a hole in the graph right here. Okay? Just bear with me and watch this. So there's a hole in the graph right there. And that's going to be 1, 2, -1. So there's a hole at 2, -1. Okay? Now, if I asked you for the domain, remember, this is slowly getting wider. This is slowly getting wider, okay? So there's no vertical lines I can draw. However, there's a break in the domain, and it's right here. So I could kind of draw a vertical line right here through that point, because there's a break there in the domain. So see if this makes sense. My domain would be, to watch, negative infinity all the way until I got to here, and that would put a 2, and then put a comma, because it's non-inclusive, and then the domain would pick up again at where? 2, non-inclusive, and continue on to what? Positive infinity. Do you see that? Because there's a break there, the domain would come from negative infinity all the way to 2. There's a break there, non-inclusive, and then from 2 all the way on. Now the range we said is what? I think we said the range was at -2. Now, think about the range for a second, guys. The range is going from here to here, alright? This is going to be difficult to see, but there is no break in the range. Mr. Error, you're wrong, it's right here. But guys, yes, there was a break here on the x-axis, okay? At 2. But look, you're telling me that on the y-axis, there's a break right here. But I'm telling you where this break is here. Over here, there's a solid point, and that's going to take care of that y value right there. Think about it, guys. Look, I'm going to put it to you like this. I think this will help a lot. Watch. This is -2. This is 2, -1. And we're going to call this -2, -1, okay? Now, at this point here, -1 does not exist on the graph, it's open. But over here, your y value of -1 does exist. So there's no break in your y values, okay? So your range would still be from here, -2 up to positive infinity. We'll do a lot of these in your homework. You'll get some practice, okay? But you need to be able to analyze graphs and tell me the domain and range. We're going to practice more of these in your homework, okay? Next, let's take a look at deciding if a graph represents a function. Now, this should be pretty easy, and it should also be pretty familiar from Algebra 2 and Algebra 1, okay? Here we go. We do this by running a test. Remember this? It's called the vertical line test, and you should remember this, okay? So we call this the vertical line test. Now, let's take a look at 4 examples on page 80. So instead of drawing all of these graphs, I would make a note in your notes that we're going to do with the 4 examples on page 80, okay? This will probably be the easiest thing we do all class period, alright? So here we go. Let's take a look at our first example here. Now, the vertical line test is this. I'm not going to give it to you in words. I'm just going to explain it to you, okay? The vertical line test says this. If there is anywhere that you can draw a vertical line, anywhere in which this vertical line intersects the graph in more than one place, then the graph does not represent a function. So, for example, here's my graph right here, my parabola. Does that graph represent a function, yes or no? Well, is there anywhere that you can draw a vertical line that intersects the graph in more than one place? Well, sure, right here. In fact, there's quite a few. There's a lot of vertical lines you could draw that intersect the graph in more than one place. All of these vertical lines are intersecting the graph in 2 places. So, because of that, we can confidently state that this graph is not a function. Okay? It's pretty simple. I mean, it's like this. If you can draw vertical lines and see how many times they intersect the graph, then you can do this vertical line test. By the way, you do not need to take notes on this, but see if this makes sense real quick. I'm going to explain to you why or how the vertical line test works, okay? This ordered pair is -2.5. And it's up about 3.5. Okay? This ordered pair here is -2.5. And it's up about 1/2. Now, students, look. This is your input. This is your output. This is your input. This is your output. Look, your input, -2.5, had 2 outputs. Do you see it? Your input is -2.5. And it had 2 outputs. It had an output of 3.5 and an output of 1/2. Anytime 2 points are directly above and below each other, vertically like this, that means you're going to have 1 input with 2 outputs, and that's why the vertical line test works, okay? Alright, let's go ahead and take a look at the next example. I'll go a little faster now, okay? Because these are really pretty simple. Alright, now, this one here does represent a function. It does. Is there anywhere you can draw a vertical line, anywhere, that intersects the graph in more than one place? No. Every vertical line that you draw intersects the graph in only one place. One place. One place. So yes, this graph does represent a function. Okay? Alright, next example. Now this one could be confusing because here you can draw a vertical line that does not intersect the graph anywhere, but I never mentioned that to you. All that I said is there anywhere you can draw a vertical line that intersects the graph in 2 or more places, or more than one place? And the answer is no. I don't care how many vertical lines you draw, every vertical line is going to intersect the graph in one place. One place. One place. So yes, this graph does represent a function. And then lastly, example number 4. is there anywhere you could draw a vertical line that would intersect the graph in two places? And immediately students yell out, yes, yes, right here, Mr. Earhart. No, I'm sorry, that's not true. That vertical line does not intersect the graph in two places. It intersects the graph right here. But this open point is not part of the graph. In other words, it's like this. The line went to here, and then the other line started over here. There's a little bit of a gap there, okay? This is not part of the graph. I know that. How do I know that? I know that because it's an open place, an open spot, okay? So, every vertical line that I draw is intersecting the graph in one place, every single one. So yes, this graph represents a function. So let's quickly review. This is called the vertical line test, okay? And vertical line tests tell us whether or not a function represents, whether or not a graph represents a function. Okay, moving on. Now, let's take a look at finding the zeros of functions. Now, I want to give you an amazingly important statement, and I hope that you will listen to me and take really good notes. This next comment is so important. Here it is. Before we do that, I'm kind of repeating myself, sorry. I want to be very clear about something, and please don't ever forget this. Okay, so here it is. Copy this down. Finding the zeros of a function is the exact same thing as finding the x-intercepts. So, if I say to you, find the x-intercepts of this function, you're really finding the zeros. And if I say find the zeros of the function, you're really finding the x-intercepts. Okay? So you can use these phrases interchangeably. Let me tell you why we call these zeros of a function, okay? We call them zeros because we're looking for values that you're going to put in for x or y that will give you out 0 for the x, okay? And I think I said that backwards, and I apologize. Hold on. That's totally wrong. We're looking for x values that when you put these x values in, you get out zeros. For example, what is the 0 of this function right here? Well, that's obvious. The 0 is -2, because what value could you put in for x that would give you out a 0 for the whole function? Well, -2. If you put a -2 in for x, -2 plus 2 is 0, so y equals 0. So that's why we call them zeros. We also call them x-intercepts. And think about it. This would be an x-intercept, -2, comma 0. We put -2 in, we got out 0. So this is an x-intercept, but it's also called a 0 because -2 gives you out a 0. So please don't ever forget that. Zeros are the same thing as x-intercepts. Let's find the zeros, or what else can we call it? X-intercepts of these three functions. Alright, number one, let's find the zeros of this function. So here's how you do it. Now if you'll listen to me, I will teach you how to do this and give you really good notes. So please pay attention if we're going to find the zeros. That's the same thing as finding the x-intercepts. And remember from algebra class, whenever you're finding the x-intercept, you put 0 in for y. Remember, if you're finding the y-intercept, you put 0 in for x. So I'm looking for the x-intercept, or zeros. So I'm going to put 0 in for y. F of x is the same thing as y. So I'm going to put a 0 right here. Now, hopefully, you guys remember how to factor this. Okay? We should. If it is factorable, which I hope that it is, and it is, remember, we have a trinomial here with a lead coefficient of 3. Now I'm going to go fast. We covered this the first 2 weeks of school, and I told you we'd have to know how to factor the rest of the year super quickly. So you take your first term times your last term, -30. Well, two numbers multiplied together give you -30. When add together give you a +1. Well, that's +6 and -5. Okay? When you multiply them, you get -30. When you add them, you get +1. So you bring down your first term. You bring down your last term, and right in the middle you put +6x from this and -5x. Then pull out what's common in the first two. 3x times plus x is 3x squared. 3x times 2 is 6x. Then here you pull out what's common, and if this term's a negative, you pull out a negative 2. If it's a positive, then you pull out a positive, okay? So, pull out a negative 5, and you're left with x plus 2. Negative 5 times x, negative 5x, negative 5 times 2, negative 5, 2. Write your matching parentheses once, and you're left over with 3x minus 5. So there we factored it. Now all of this, remember, equals what? 0. Equals 0. Equals 0. Now, if you take this group, set it equal to 0 and solve, you'll get negative 2. If you take this group, set it equal to 0 and solve, you'll get this right here, 5/3. Or same thing as 1 2/3. So there's the zeros. There's 2 of them, negative 2 and 5/3. Okay, so that's how you find the zeros of a function. You put 0 in for y and you solve. Not too difficult. By the way, I've got the graph here to prove this to you. So I'm telling you the zeros are what? Negative 2, 1 2/3. But I'm also telling you that those zeros are the x-intercepts, right? Well, let's see if I'm right. Here's the graph of this function right here. There it is. Oh, look at that. Looks pretty good to me. There's one x-intercept, negative 2. There's the other x-intercept, 5/3. Exactly like we got out, okay? Alright, now let's find the x-intercepts of this function here, okay? Now remember, we put 0 in for y. Now, how do we get rid of a square root? If we're solving for x, then we need to get rid of this square root. Well, we're going to square both sides. So if we square this side, we get 0. If we square this side, anytime you square a square root, you get the radicand. Now bring the 10 over and make it a negative 10. Now divide both sides by a negative 1. And now take the square root of both sides. The square root of 10 is positive negative square root of 10. The square root of x squared is x. Okay, now the square root of 10 should be 3.1 something, okay? So I'm claiming the x-intercepts of this graph right here would be positive negative 3.1. Well, here's a picture of it here. Let's see if I'm correct, okay? There's your x-intercepts. Look at that. Negative square root of 10, positive square root of 10. There's the graph of this function. Okay? Alright, moving on to the last one. Let's find the zeros of this function here. Alright, well, for h of t, we're going to put 0. So 0 equals 2t minus 3 over t plus 5. Okay? Now, pretend, remember students, you can put anything. Well, I'll tell you what, I'm going to approach the problem like this. I don't want to have this fraction over here, so I'm going to multiply this side by t plus 5. But if I multiply one side by t plus 5, I must multiply the other side by t plus 5, okay? Well, anything times 0 is just 0. Over here, these would cancel, leaving you with 2t minus 3. Bring the 3 over and make it a positive 3. Now divide by 2, and we get 3 halves equals t, or 1.5, or 1.5. So, we put 0 in for y, and we got out our x-intercept, or our zeros. So 3 over 2 would be your 0, which is also your x-intercept, okay? And real quick, let's take a look at the visual that we have, and let's see if we're right. Okay, this is a visual. This is a graph of that function. There we go. Here's the x-intercept right here. And what is the x-intercept? 3 halves, okay? Not too difficult. Alright, let's stop and review for a second. So far we have learned how to find the domain and range of a graph. Next, we learn how to prove whether a graph is a function by using the vertical line test. And now we have learned how to find zeros of functions, or x-intercepts. Okay, moving on. Only 3 more topics, and then a new intervals of graphs, okay? Increasing and decreasing intervals. Here are 3 examples. Now, I would make note in your notes that you can find these graphs on page 82, okay? We're going to do 3 examples on page 82. Now, I probably should have typed something, students, that I didn't type. I think you need to write this down, so let me go ahead and just get rid of this real quick. I should have typed this, okay? When you're dealing with increasing and decreasing intervals, please listen to me carefully. How's the best way to word this? You base I would write this down if I were you. You base the numerical intervals on the x values, not the y values. That's really, really, really important. And by the way, every year students get confused on this and they make the mistake and they use the y values. When you're dealing with increasing and decreasing intervals, you use the numbers on the x-axis, the x values, not the y values, not the y-axis. Okay? Alright, I'm going to go ahead, in case some of you are still copying this, I'm going to slide this over here. And here we go. Alright, now, let's take a look at this and see if we can find increasing or decreasing. By the way, you always read it left to right like it's a book, okay? So, going left to right, starting at the left and moving to the right, it's going up. So it's increasing, increasing, and it looks like it flattens a little, but it really doesn't. I mean, it keeps right on increasing. I mean, from here to here, it goes to 0, then to 1, or to 0.1, and it keeps going. So this graph is constantly increasing. So if I asked you for the areas on this graph where it was decreasing, you would say none. In fact, make a note of that, please. This graph does not decrease at all. Well, Mr. Earhart, how would it decrease? If it took a curve like this and started going down, then it would be taking a decrease. And if it curved back up, that'd be an increase. And then a decrease, then an increase, so on and so forth, okay? But we don't have that. We have an increase. You always, with Mr. Earhart, going from here to here, it's going down. True, but that's going from right to left. And I said go from left to right. So you start on the left side, just like you're reading a book, and you go up, okay? Or excuse me, you go over to the right from left to right. Now, students, we are to assume as the graph continues downward, it's still going to get wider and wider and wider. And as it continues upward, it's going to get wider and wider and wider. So the graph is increasing. Remember, we use our x values. Well, it's getting wider and wider and wider, both directions. So the increase would simply be what? You guys know. Negative infinity to positive infinity. Now, let's pretend for a second that there is a point, a stopping point. Let's say in the book, they put a point here. And let's pretend it was even with 1. So here's positive 1. Unless there's a stopping point here, even with negative 1. Well, these are the x values. So you would say it's increasing from negative 1 to positive 1. Because here's where it starts, and it's even with what x value? Negative 1. And here's where it stops, and that's even with what x value? Positive 1. So you would say the graph was increasing from negative 1 to positive 1. And see, that's where students get confused. They forget to use the x values. You use the x-axis x values only when you're writing increasing and decreasing intervals, okay? Alright, let's try 2 more. I think that will really, really help, okay? These are not too difficult if you just practice and really pay close attention and not make little mistakes, alright? So here we go. Now, this is a pretty interesting graph. First of all, from here to here, left to right, it's increasing. And it's increasing until it hits this turning point. So let's go and put the word increasing. Take some good notes on this, students. It's increasing from, well, we start to the left, and we're assuming the further it goes down, the further to the left it's going. So it's going to continue to get wider. So it's going to increase from what? Negative infinity to, now, to this point here. Now, are you going to use the y value too? or you're going to use the x value -1. Remember I told you, always use the x values when you're writing increasing and decreasing intervals. So this thing is increasing. This thing is increasing from -infinity to here, which is even a -1. And by the way, here's another note you should write down. You always use parentheses for increasing and decreasing intervals. There are no inclusive and non-inclusive. But you know why? Because who knows? At this point here, is the graph increasing or is it decreasing? It's nothing. That's the actual turning point. So we can't really call it inclusive for increasing, and we can't call it inclusive for decreasing. So when you're dealing with increasing and decreasing intervals, always use parentheses, no brackets. Please don't forget that. Okay, moving on. Now, so from here, let me change colors here. From here to here, it's now decreasing until it hits this point right here. So it was decreasing from, well, we start with the x-axis, so -1, all the way to here, and we use the x-axis value, not the y. So from -1 to +1, it's decreasing. And then from here up, it's increasing. Alright? It's increasing. So we have another increasing value. Now it starts here, which is equal to 1 on the x-axis. So it's increasing from it's increasing from 1 to infinity, because the graph is getting wider and wider as it goes up and up. It's getting wider and wider to the left, or to the right, So here's your increasing intervals. Here's your decreasing intervals. Okay, not too bad. Let's take a look at one more. Alright, now, let's take a look at this. Reading it from left to right. Now, there's no point here. Okay? So, we cannot assume that it stops there. So we are going to assume that it continues on and on. Alright? So, from here up, it's increasing till it hits this point here. So increasing is from -infinity to this point here. And of course, where is this point? Even with on the x-axis, 0 right here. So -infinity to 0. Now here's something new. We call this constant. So now there's an interval where the graph is constant. It's not increasing and it's not decreasing. So it's constant from here to here. Now what is your x value? 0. What is your x value? 2. So it's constant from 0 to 2. Okay? Then from here down it's decreasing. Decreasing. So it's decreasing from, well, it starts here, which is even with what number on the x-axis? 2. So it's increasing from 2 to infinity, because the graph continues on and on down and over to the right. Okay, so there we go. So I hope that makes sense, students. So far I hope I don't forget anything. I'm going from my memory. So far we have found the domain and range of graphs. Then we used the vertical line test to prove whether graphs are functions. Then we I'm going to have to cheat a little bit. I forget what was it. It was, we found increasing. No, let's see, what else did we do, guys? We did, we found the zeros of functions. And now we just learned how to find increasing and decreasing intervals of graphs, okay? Moving on. Next, let's take a look at something called relative maximum and minimums, okay? So make note of that. Relative maximums and minimums. Now, understand, and you might want to write this down, it's up to you. Understand that a maximum or minimum point occurs when there is a turning point on the graph. Got it? There has to be a turning point in order for there to be a maximum or minimum point. If there's no turning point, then you cannot have a max or a min. Let me demonstrate, okay? This picture will help you a lot, okay? Notice the graph has a turning point here. Notice the graph has a turning point here. Notice it has a turning has a turning point here. So whenever there's a turning point, we then have either a maximum or minimum point. Now, see how this thing is curving down then up? So we call this a minimum, okay? A minimum point, because it's low. Then as it comes up here and it goes from increasing to decreasing, we call this a maximum point right here. Because it's kind of like a hump going upward there. Then here, this would be a minimum because it's like a hump pointing downward. Okay, that's a low point. That's your minimum. And then up here would be a maximum. So this graph has two minimum points and two maximum points. Will the number of minimum and maximum points always equal each other? No, not at all. Not necessarily at all. Okay? That's just a coincidence. Now, with that in mind, here's what I want you to do. I want you to find the maximums and minimums of this function. However, we are going to use our handy dandy cool calculators, okay? So please get out your calculators and turn them on, which is always a good thing to do when you're going to use your calculators. And let me show you how to find maximums and minimums using your calculators, okay? So we're going to find the maximums and minimums of this function here. Now, if you will please follow these instructions carefully, you will be fine, okay? But I need you to follow these instructions very carefully. If you get lost at all, just pause the video and back it up. To me, it's common sense that we cannot use our calculator until we first enter this into our grapher mode. So, at the top left of your calculator, you'll see the y equals little button. Hit that, and then type this equation into your calculator right here. 3x squared, you hit a 3, then hit x, then hit squared, then minus, then 4, then x, then minus 2. If you don't know where the x button is, I will tell you where it is. It's the second column over from the left. So your calculator's right here. Here's your calculator. Here's column number 1, here's column number 2. It's the second column, and go down the second button, and you'll find it right there, okay? That's your second column, second button down from the top. So step 1 is to enter this equation, okay? Once everyone's done that, if you need to pause the video, pause the video. Once everyone's done that, let's continue on, okay? So, now the next thing we want to do, students, is we want to hit the word graph. But before you hit the word graph, I want you to go to the very top button, second from the left. It says window. Okay, go ahead and push window. No, I'm sorry, not that button. Sorry, go one more to the right, zoom button. Push zoom, okay? After you push zoom, scroll down to option 6. Option 6 should say Z standard. Now it's going to give you a standard window of 10 to the left, 10 to the right, 10 up and 10 down. So go ahead and hit option 6. And when you do that, the graph should appear on your screen, and it should look like this. If it doesn't look like this, then you've made a mistake somewhere, okay? It should look something like that, similar to that, okay? Now their windows are a little different. They're using -4 and 2, but for the most part, it should look like that, okay? Now, here's how you find the minimum. Now notice, we have a turning point here. So are we looking for a minimum or a maximum? We're looking for a minimum. So now that your graph is on your screen, I want you to look at the top buttons. You see a little button to the right, way up top. It says trace. T-R-A-C-E. It's way up at the top. Second button from the right says trace. Well, do not push trace. I want you to push your shift button or your second button. Push that first and then put trace. And when you do, this is what should pop up. You should have a screen that has options. Option number 1 should say value. Option number 2 should say 0. Option number 3 should be minimum. There it is. Option 3. So you can scroll down to 3 and hit enter, or you can just push the number 3. Now when you do that, here's what your screen's going to say. If you have to back any of this video up, please feel free to. Somewhere on the screen it should say left bound question mark. Left bound question mark. And what you do is somewhere in the graph you should have a little flashing cursor. Should be a little circle thing flashing at you like this, flashing. No, I'm not sure if you don't see it. If it's not, on your screen, then you know how you have your arrows at the top right of your calculator. You have an arrow pointing this way, an arrow pointing that way, an arrow pointing that way, and an arrow pointing that way. Okay, well the arrows you want to use are these two, not the up and down. You want to use left and right, okay? Now it's saying left bound, so if you don't see that flashing cursor, then push the left or right button a couple times until you see it appear on the screen. Now when you do, because your screen says left bound, you want that cursor, here's your minimum right here, got it? There's your minimum. You want your cursor to be somewhere over here on the left side, okay? It's got to be somewhere over here on the left side. So, if your cursor is somewhere over here, go ahead and hit enter. When you hit enter, now it's going to say right bound. Do you see that? So students, now that your calculator says right bound, you want to use your right arrow button and move that cursor somewhere over here. Okay, sorry, there we go. Move the cursor somewhere over here on the right side of this point right here. So make sure it's over here somewhere. Okay, once you've moved the cursor anywhere over here, then push enter. Okay, let's push enter. Now it's going to say this on your screen. Guess, which is what a lot of you do on your tests and quizzes. Just kidding, I'm joking. But just hit enter. Just hit enter, okay? And when you do, this should appear at the bottom of the screen. X should say 0.66666. And it should say y equals -3.3333. Now students, when you have repeating decimals like that, it's really safe to assume what you really have is this. X is 0.6 repeating, so X would be 2/3, okay? And Y would be -3 1/3, or negative 10/3, okay? So there we go. That would be your minimum point right there, okay? The students were only doing one of these, however, you'll get plenty of practice these in your homework, okay? Alright, let's continue on. Now, if I can get this to work, it's acting really weird tonight, guys. There we go. It's freezing up. Okay, lastly, before we look at a new special type of function, let's look at what even and odd functions are. Please take some really good notes, okay? An even function is a function that is symmetric to the y-axis. Please copy that in your notes. An odd function is a function that is symmetric to the origin. I'm going to pause while you copy these two definitions down, okay? Even function is a function that is symmetric to the y-axis. Odd function is a function symmetric to the origin, okay? Please copy those two definitions down, guys. You need to know that. You need to know that. Take a second and copy those down, please. Let's continue on now. Let's take a look here at, I want to give you some visuals, okay? So let me give you some visuals of what these functions will look like, and then I will teach you a method to help you decide if a function is even or odd. But first, the visuals, okay? So here they are. Now again, you don't have to write these down. If you want to make note, these are in your book, and they're on your book on page. Give me just 1 second, please. I should have written this down. You'll find them on page 86. If you want to make note of that, page 86 now. Notice this. this graph here is symmetric to the origin. And here's why. Every point that appears on this graph has another point that has the opposite signs. For example, if this point here appears this point here lies on the graph xy, then somewhere on the graph negative x, negative y appears. Okay, let me show you. I'll make that a little better to understand. Look at it like this. Okay, if this let's pretend this point here is 2. Just pretend that this point here is 2, 3. Okay, well, if 2, 3 is on the graph, then you know for sure somewhere negative 2, negative 3 exists, which would be negative 2, negative 3 down here. Okay, now let's pretend this point here is negative 1/2, 1/2. Got it? So if that point exists, then change both of those signs. That means positive 1/2, negative 1/2 exists, which would be right here, positive 1/2, negative 1/2. Okay, so every point that exists on this graph, we know that you can change the signs of those two numbers, and that point will also exist on the graph. Another way to know that you have origin symmetry, and by the way, that's what this is, so make note of that. That's origin symmetry. Another way to know is if you folded this piece of paper right here, and the graph fell over here, and then you folded it again on this line, the graph would fall. Trust me, the graph would fall right on top of each other. It would, okay? And so that's another way to know that you have origin symmetry, okay? Let me give you a picture of y-axis symmetry, or symmetry with respect to the y-axis. Okay, it's really simple. It just means that if you were to fold a piece of paper right on the y-axis, then the two sides of the graph would fall on top of each other, and they would. But another way to recognize it is the ordered pairs. Whatever ordered pair exists, you can change the sign of the x, and that ordered pair will exist also. For example, let's pretend that we have 3, 6 right here. Got it? 3, 6. Well, if 3, 6 lies on this graph, change the sign of the x value, just the x value only, you're guaranteed that negative 3, 6 also appears. Now it's not, obviously, because that we just pretended it was, but there it is, negative 3, 6, and that will continue on and on. Okay, let's pretend we have negative 1, 2 right here. Well, if negative 1, 2 exists on this graph, change the sign of the x value, then that means positive 1, 2 will also exist, and it does right there. Okay, so that's called y-axis symmetry, or symmetry with respect to the y-axis. Okay, I'm giving you an unbelievable truckload amount of notes today, but it's good for you. Okay, we've got to learn this stuff. So there's some visuals. Now let's get into the method, okay? So take some really good notes, please. We're almost done. Alright, I want us first of all to check these two functions to see if they are even or odd, or maybe neither, okay? So let's start off with this function right here. Here's what you do. Please take really good notes. First of all, substitute y in for g of x. That's the first thing you want to do. Now, to check for origin symmetry, everywhere there's a y and everywhere there's an x, you put a negative y or x. So here's a y, I'm going to put a negative y. Here's an x, I'm going to put a negative x. Here's an x, I'm going to put a negative x. Next, so that's simple, guys. Everywhere there's a y, you put a negative y. Everywhere there's an x, you put a negative x. Then you simplify, so negative y is just negative y. Negative x cubed, that's negative times negative times negative. That's going to be negative x cubed. Then negative times negative is positive. Okay, let's review. Everywhere there's a y, you put a negative y. Everywhere there's an x, you put a negative x. Then you simplify and then get y by itself. So to get y by itself, we're going to go through and change all the signs. So y equals, that'd be a positive and then a negative. Now, you know that you have origin symmetry if, after you've done all of that, you get out a function that is identical to your original function. Is this function here identical to this one? Yes, it is. So we know that we have origin symmetry. Okay, we do have origin symmetry. Now we also might, so what do we call, I better back up. So what do we call that? We say this function is odd. Remember the definitions I gave you? Let's go back a page. Odd functions are functions that are symmetric to the origin. Now this graph could also be symmetric to the y-axis, possibly so. Let's see what we have here, okay? How do you test for y-axis symmetry? Well, I'm going to show you. First of all, go and put y in like we did before. Now, when you're checking for y-axis symmetry, everywhere there is an x, you want to put a negative x. You leave the y alone. Now, when you take negative x times negative x times negative x, you get negative x cubed. Negative times a negative is a positive. So I simplified. Now, is y all by itself? Yes. Is this function here identical to your original function? Not at all. So we know that we do not have y-axis symmetry. Let's try another one, okay? Let's come over here and try our last problem before we get into a new type of function, and then we're finished, okay? Now, let's check this for origin symmetry. So I've taught you to do that. Everywhere there's a y, we're going to put negative 1, or negative y. Everywhere there's an x, we're going to put a negative x. Okay, let's simplify. A negative y is just a negative y. Negative x times negative x. Negative times negative is a positive. Now, y is not by itself. Go through and change all the signs. Now, is y all by itself? Yes. Does this function here match this function here identically? No, it does not. So we know that we do not have origin symmetry. Maybe we have y-axis symmetry. To say everywhere there's an x, I'm going to put a negative x. Okay. Well, negative times a negative is a positive. So y equals positive x squared plus 1. Does that match the original function right up here? Yes, it does. Perfectly. So we know that we have y-axis symmetry. And what do we call y-axis symmetry? It's an even function. So we know this function right here is even. Okay? Let that sink in. Back it up if you need to. Make sure you take really good notes. And I'm going to go ahead and move on. Now, as we wrap up today's video, I want to talk to you about a function called the greatest integer function. If you've ever had these before, sometimes they can be really dreaded, but if you'll listen and take really good notes, you'll be fine. These are not that difficult. First, here is the symbol for the greatest integer, okay? It's like this. I'm going to draw it really big so you can see it's like this, and then with a line here, okay? And like this. So it's almost like a bracket with a double line, okay? Now you know, if you see something like this, you know that means the absolute value of negative 4. Well, if you see something like this, that means the greatest integer of negative 4. I'm going to talk about what that means, okay? But that's the symbol. Do you see the symbol? It's like a bracket with a line going down here. A bracket with a line going down here. That's the greatest integer symbol. Got it? Second, here's what it means. It means the greatest integer less than or equal to x. Now that's a book explanation. I'm going to give you a much better explanation of that in just a couple minutes here, okay? But go ahead and write that down. It's good notes. It means, technically, the greatest integer less than or equal to x. That's what it means. I'll explain that a little better in a couple minutes here, or a couple seconds, but go ahead and write that down. Now, moving on, lastly, let's try to graph one of these types of functions, okay? So here we go. Here's the function we're going to graph. Y equals the greatest integer of x minus 2. Now guys, look, we're going to start off off with using a table of values. Let's say we're going to put in something like, I don't know, -5, okay, for x. Now, what this means, by the way, you know what absolute value means, right? If I have the absolute value of x minus 2, you know that simply means every number I put in for x, I get out of what type of number? A positive number, right? You know what absolute value means? Well, greatest integer means something too. It has a meaning, and what it simply means is this. I'm going to show you, okay? If you put in, let's start off with the whole number, -2. If you put -2 in, that's already an integer, so you will get out -2, okay? And by the way, if you've forgotten what an integer is a whole number, negative and positive, so -5, -6, -2, -3, 1, 2, 3, 4, those are all integers, okay? They are numbers that don't have decimals or fractions. So if I put -2 in for x right here, I would get out of this -2 also. And then you have to subtract 2. So if I put -2 in, I would get out -4. Now I hope that's not confusing. It shouldn't be too bad. I put in an integer, so I simply get out an integer, okay? Now here's where it's going to get tricky, so pay attention. But when you're dealing with integer functions, you have to really think this through, okay? And we got to use numbers that are not integers so that we get a really good picture of the graph. So now I'm going to try -2 point. Let's see here. Let's go with, now students, the best thing to do here, now listen to me carefully, to know what value to put in next when you're dealing with greatest integer functions, listen to me please, is to use a number line. Please listen to me, I will help you, okay? This will make sense. Here's 0, -1, -1, -2, okay? Now, we just put -2 in for x. Usually you put it in a table of values here. We'll put an x and a y here and put a table of values going down. Usually you put whole numbers in next, like -1, 0, but not when you're dealing with greatest integer functions. You want to work in decimals. Now we don't have to do a lot of these, but just watch. What you want to do is you want to work your way to the right on a number line, okay? So the next value I'm going to put in would be like negative, let's say 1 point, I don't know, -1.8. Alright, -1.8. Now, whenever you put in -1.8 in for x right here, okay? So we're putting a -1.8. Remember, this is called a greatest integer symbol. So whenever you put a decimal into this, you have to get out an integer. You have to. So the question is when I put in -1.8, do I change it to a -2, or do I change it to a positive or a -1? In other words, I'm putting in -1.8. What integer do I change it to? And some of you might say, oh, we changed it to -2 because we would round to -2. Well, you're right and you're wrong. You're right that it's going to come out -2, but the reason it comes out -2 is not because you're rounding. It's because, here it is, are you ready? Whenever you put a decimal into a greatest integer bracket, you always go to the integer to the left, period. So if I'm at 1.8, which integer's to the left? -2. So if I put a -1.8, it comes out of this -2, and -2 and -2 is -4. So if you're thinking here, guys, anything that you put in between -2 and 1 is going to come out -2. Let's put in -1.1. Okay, so if I put -1.1 in to my greatest integer right here, if I put in -1.1 into this box right here, what would have to come out? Where's -1.1? You always go to the left. Go to the nearest integer to the left. So the nearest integer to the left is -2. So -1.1 comes out of that box -2. And then -2 minus 2 would be -4. So I think you're getting the picture here, guys. Any value, I shouldn't have done that, sorry. Any value that you put in for x between -2 up to -1, you're going to get out -4. Now let's put in -1 real quick. Well, when you put -1 in, you get out what? -1, because -1's already an integer. So put negative 1 into the greatest integer box. Out comes negative 1. Bring down your negative 2 and you get negative 3. Now let's continue to the left. Let's put in 0.5, negative 0.5, okay? Negative 0.5. Well, if I put into this equation right here, this function, if I put into this negative 0.5, then go to the left, always go to the left. What's the first integer you get going to the left? Negative 1. So negative 0.5 comes out negative 1. Negative 1, negative 2 is negative 3. So I don't care what value you put in for x. Between 0 and negative 1, you're going to get out negative 1. Then bring down your negative 2. You're going to get negative 3. Let me do one more set. Let's put in a 1. I want to put a 1 in, okay? If you put a positive 1 in to a greatest integer box, you will get out what? Put in a 1, and you will get out a 1, because 1's an integer, and then 1 minus 2 would be negative 1. Now let's continue to the right, and let's put in, okay, students, here we go. Now, let's continue on here. Sorry about that. My wife asked me a question and I forgot I was videotaping. Okay, so if we put a 1 in, we get out a negative 1. We put a 1 in and we get out a 1. 1 minus 2 is negative 1. Now, let's put in a 1.5, okay? So if I put 1.5 into my greatest integer bracket here, always go to the left. So what's the nearest integer going to the left? 1. So if I put a 1.5 in, it comes out a 1, and 1 minus 2 is negative 1. So if I put a 1.5 in, I get out negative 1. Now here's what I want to show you. I want us to graph this, just a little bit of this, and I think you're going to see it, okay? Hopefully you'll see this, okay? Okay, this here. Now, okay, now let's go to negative 2, negative 4, got it? So negative 2, negative 4, there it is. Now, negative 1.8 is also negative 4. Negative 1.1 is also negative 4. Here's what I want to show you. Any value that you put in for x from negative 2 to 1 is going to give you out negative 4. So really the graph goes from here to here, just a straight line going across. However, when you get even with negative 1, you have an open point there, because look what negative 1 gives you out, guys, right here. Negative 1 gives you out negative 3. So at negative 1, we're at negative 3. So we put this. Now please understand, students, anything, look at negative 0.5. Negative 0.5, which is right here, gives me out a negative 3. Negative 0.5, negative 3. So what I want to show you is any x value that you put in from 1 to 0 is going to give you out negative 3. So we have a line going across here until we get right to 0. Then we have an open spot, because if you put a 0 in, the greatest integer of 0 is 0. 0 minus 2 is negative 2. So when you put in 0, you'll get negative 2. And by the way, any x value from 0 to 1 that you put in will give you out negative 2. So all of these values will be negative 2 until you get to 1. Then you put an open spot there. Why? Because when you put 1 in, you didn't get out negative 2. When you put 1 in, you got out negative 1, which is right here. Okay? And then it continues. Look, any value you put in between 1 and 2 is going to give you out negative 1. So it continues on until you get to here. Then you put an open spot. And this continues on. And by the way, this is a form of a step function. Doesn't it look like stair steps? We call this a step function. There are many step functions. This is one type of step function, okay? So this is the greatest integer function. This is a good introduction to this new function. You will get some problems to practice in your notes where you graph this, okay? I know this has been a ton of notes. It's good for you guys. It's not going to hurt you. If you have any questions, I hope this video has been a help to you. If you have any questions, don't hesitate to call or email.